My presentation has three topics. First, prediction of seismic intensity on the ground. Second, seismic design of buildings in Japan and their seismic performance. Three, safeguarding in rooms for earthquakes. Let's go into the first topic. This is a map, earthquake map in Japan. You can see many epicenters located in the ocean side of Japan Island. We use the seismic activity factor in seismic design. And, the severest active zone in color in red, including Tokyo, located in ocean side. The activity factor in yellow zone, including Sapporo, is reduced 0.9, and it is reduced 0.8 in green zone. We call this map a macro seismic zonation map. However, seismic activity is different in small area. For example, Sapporo. This square frame has 10 kilometer by 10 kilometer. Here is a Sapporo station. Seismic intensity observed Kushiro-oki earthquake is different from 3- in blue and to 4+ in red. So that we have to get the micro seismic zonation map, not macro seismic zonation map. This is a transmission mechanism of earthquake waves. Earthquake wave is radiated from a fault and propagate under the ground. Finally, shake the site. We know that ground motion at the site is in proportion to the magnitude of seismic cause, and it is in inverse proportion to the distance from seismic center. Vibration behavior of ground surfaces is condition of ground subsoil of ground. At the point A on mountainside, vibration on the ground shows period and a small intensity because it's on hard ground. At point B and C, the vibration shows the middle ones because they are on the normal ground. At point D, on soft ground, intensity of vibration becomes very large. Therefore, we can say the softer the subsoil ground is, the larger the period is, and the larger the ground motion is. This is a surface geological map of Sapporo. Red line is JR line, and Sapporo station is here. Light blue means soft ground, and brown means hard ground. This building is just here on the hard ground. And we can see the soft ground distributed in the north side of JR line and a part of west side. These areas show large ground motion in earthquake. This is the supposed seismic sources around Hokkaido prefecture. Red lines are active fault, and round mark plate boundaries based on the theory of continental drift. Seismologists can estimate seismic intensities in any site by calculation using these maps. This is an estimated seismic intensity map in downtown of Sapporo area. There are these numbers is the seismic intensity level used in Japan. Level 7 in color in red means the severest ground motion, which are located in west side and north side. This building just here on the sixth lower level. This map is called as a micro seismic zonation map. Japan Meteorological Agency uses the seismic intensity scale with 10 levels from 0 to 7. The unit is called as shindo. For example, the shindo 5 lower, many people try to escape a danger and books and dishes fall. And 6 upper, many people are impossible to keep standing and to move without crawling. And and unfixed furniture moved and falls. And also the low earthquake resistant houses collapse. The level 6 is maximum. All people are impossible to move at will. The shindo 5 lower and upper is called as middle earthquakes. And shindo 6 upper and 7 is called as earthquakes, large earthquakes. Please remember this word because I will use later. The second topic is seismic design of buildings in Japan and their seismic performance. The present seismic design code of Japan is consisted of 2-step calculations. In the first step calculation, the structures of buildings must be the performance to be used continuously without any repair after middle earthquakes, which occur once about 50 years. In case of a reinforced concrete structure, during middle earthquakes, small deformation, and narrow cracks are accepted. However, after the earthquakes, these deformation and cracks must be reduced. In the second step calculation, the structure of the buildings must be keep the human life instead of acceptance of severe damages during large earthquakes, which occur once about 500 years. During and after large earthquakes, unrepairable damage like this is acceptable, as long as all inside spaces in structure are kept. However, crashing at any story is not acceptable because the human life is lost here. This apartment house collapsed in Kobe earthquakes. The left side was crushed at this floor. The the building standard of Japan does not permit like this collapse. The other hand, the right side was not crushed. So the standard permit like this severe damage because nobody died in this area. Seismic design techniques have been improved in every earthquake event. The building standard of Japan was publicated in 1950. The seismic design code in the standard was applied to only middle earthquakes. In 1968 Tokachi earthquake, many reinforced concrete school buildings collapsed, so that the code improved a little, such that the design of reinforced concrete columns and foundation was intensified. In 1978, Miyagi-ken earthquake, very large acceleration on the ground were observed. Therefore, the design code was changed drastically to apply, enable to apply to large earthquakes also. We call structures constructed before 71 as the first generation, designed by old code. And we call structures constructed from 71 to 81 as the second generation, designed by the improved code. And the structure, we call that structure after 81 as third generation, designed by new design code. In 95 Kobe earthquakes, we could compare the performances of earthquake resistance among structure of 3 generations. This is a comparison of reinforced concrete buildings suffered in the area of Shindo 7 in Kobe earthquake. The lateral axis expresses the damage level from collapse to non-damage. The degree of suffered buildings in the first generation colored in red was several percent in collapse and also several percent in large damage. But however, the degree of suffered buildings in third generation colored in blue was very small in collapse, also in large damage. The other hand, the percentage of non-damaged buildings increased from 40% in first generation to 60% in third generation. So we can take some lessons from these results. Earthquakes are vibration tests of a lot of structures with real size and many types. Seismic design methods are improved surely and will be improved more in future also. However, there are many weak buildings and houses constructed before 1981. These structures need to be strengthened as soon as possible. We have to memorize that our knowledge on earthquakes and the techniques of structural design are little and insufficient permanently, I think. The third topic is safeguarding in rooms for earthquakes. This picture is a situation just after an earthquake. A lot of bottles and dishes fell and broke. So some person will be injured later on their foot. Many furniture moved and fell down, and then they disturb the evacuation route. Some habitants may be severely injured under the furniture. This figure is a relationship between causes of accident and incidents of injured persons. Took from the Kushiro-oki earthquake. Top 3 of the causes were hot water, broken glass, and fallen furniture. There are many types of equipment against overturning fall cabinet. This type is stick type and metal fixtures and the wire or chain types. In addition to use like this earthquake-proof equipment, I think it is very important to consider the layout of furniture in rooms. So I would like to simulate the dynamic behavior of furniture during earthquake by using this layout. Here is the exit, and door opens inside. The seismic intensity level reached 5 upper. Some books and dishes thrown out, and the level go up to 6 lower. Most of dishes are scattered wider, and the television with casters moves, and slender bookshelf falls on the floor and block the exit. So someone sit on this chair, she or he will be suffered later. The level go up to the 6th upper, all furniture fall on the floor. So she or he may be severely suffered. In this case, this window is the last exit. However, if this room on the 3rd floor or upper, nobody can escape from this window. Finally, I would like to change this layout to new one, like this. So the chair is set near the main exit, and the caster of television are removed. So the intensity level go up to 5 upper. Books and dishes to start thrown out, and in 6th lower, bookshelf falls. Finally, all furniture fall down. However, the space, some space is remained here. Therefore, nobody suffered any injury. And the evacuation route can be kept in two directions. So I hope you take a presentation against large earthquakes with reference to my presentation of today. Thank you very much for the kind attention.